Heyo, it's me again. Round 2. That's where we left off. We're talking about L1. If you recall, got like a, geez, that glare is killing me. L1, our language 1. It's got disjunction, conjunction, material conditional, negation, parentheses, P's, Q's, and so forth. There's our language. Where this is the, sometimes we'll refer to it as the syntax of our language. We also have the semantics for our language. These are essentially truth tables that govern meanings of connectives. They help guide us in like evaluating expressions that are built out of P's and Q's and ors and whatnot. And we also have the proof theory for our language, which is the kind of the calculus, the rules that respect truth tables and allow us to preserve truth from premises to conclusions. Why we want to do that? Well, logic is focused on study of what follows from what within a given language. There's always a way to characterize what follows from what. The what here is truth, like truth following from truth. The premises is input, conclusions output. We want to preserve truth from the premises and the conclusions with this minimal language. And so we've divided a semantics that lets us tell when expressions are true, a syntax that the semantics provide meaning for, and then a proof theory that allows us to preserve truth through premises and conclusions. That is to say, allows us to evaluate when arguments constructed out of this language are valid. Again, validity, feature of arguments, such that if the premises of an argument are true, then the conclusion has to be true. There's no way for it to be false. Cashed out in terms of the truth table. Easy to see because we exhaust the logical space, and you can see if true, then it better be true over here. But this in a nutshell is just like you can think of it as a recipe for all logical languages. They always have like a syntax, a semantics, and a proof theory, and they're always aimed at designating or like identifying some kind of consequence. Often they're aimed at designating or like preserving, that is, consequence or logical consequence from premises to conclusions with respect to truth. So often trying to characterize how what follows from what is understood in terms of how truth follows from truth. Not all languages are like that, but many are. But all of the logical languages that you'll ever encounter do have this kind of like base format: syntax, semantics, and proof theory. So for L1, the language that we're playing with, there's a syntax, very minimal, a semantics, truth tables, proof theory. So far we've discussed those direct derivation rules: conjunction elimination, conjunction introduction, conditional elimination, negation introduction, negation elimination, disjunction elimination, disjunction introduction. Direct derivation rules that kind of respect the semantics of preserving truth for this language. And today we're going to discuss different methods, or some different methods for deriving more interesting expressions, more interesting truths from given sets of premises. And so one thing I identified last time as we were introducing the direct derivation rules is that we couldn't really easily introduce a pair for conditional introduction. So what we do have, if you notice, all these direct derivation rules for conjunction, disjunction, even negation, they're paired up. They're like, there's an intro rule and an outro rule. What we have for conditional so far with the direct derivation methods within that suite of rules is just conditional elimination. I'll remind you, conditional elimination, sometimes called modus ponens, and we're abbreviating it CEL. If you have phi then chi, you have phi, can infer chi. And so I'm just essentially, this is a rule that allows you to move from premise to conclusion while getting rid of conditional. It does it in a truth-preserving way. This is valid, right? Now, we don't have a pair. We don't have the, how do you introduce conditionals? Well, you might see this manifest in arguments like this. I might say, if P, then Q, premise. If Q, then R, premise. And I might ask you, show if P, then R. Let's think about this for a second. So, first off, intuitively, if P is true, then Q is true, and if Q is true, then R is true, then it should be the case that P is true, then R is true. So if John goes to the store, then John buys milk. If John buys milk, then John buys cake. John goes to the store. If John goes to the store, John buys milk. John buys milk. If John buys milk, if John buys milk, he's gonna buy candy. So if John goes to the store, he's ultimately gonna get some candy. And that is true. It's 100% true. I cannot be left alone in the store with candy. It's just gonna happen. It's almost trivial. Now, ultimately though, it follows, right? It seems like it should follow. If P, then Q. And if Q, then R, then if P, then R. Facts. But how do we show that? All we know how to do so far is break conditionals. So we have conditional elimination. We can get rid of these things. But we can't actually get rid of anything here, right? Because remember, for conditional elimination, it's not enough that I have if P, then Q. I have to have if P, then Q, and P. I don't have a P hanging out here. Dun, dun, dun. Similarly for Q's and R. I need to break these out somehow. How do I do it? We need a different method. We need what we call conditional derivation method. Conditional derivation method. We'll abbreviate it CD. CD is not just a simple rule like input-output. CD makes you think a little bit. You're trying to show if P, then Q. Under this method, we're going to allow you to do the following. We're going to allow you to assume P and then try to show R. So you've essentially bracketed up. You've embedded your proof inside of another proof. Now you have a new show line. I need to now show R, because if I could show R, then I could show P. Or if P, then R. Because I've assumed P is true. If I've assumed P is true, and I'm able to show R, then it just follows. If P, then R, because I've assumed P is true. So you're just going to let you have P and see what you can do with R. Now, what do we have? We have new premises to work with. We have one new premise to work with. We have P. We know how conditional elimination works, right? If I have P and if I have a P, then Q, then I can infer Q. Now I cite my method, right? I cite conditional elimination. And I need two lines, 1 and 4. 1 and 4. Conditional elimination. I've justified my use of Q. 7. Line 7, I want to infer now R. And how can I do that? Very similarly, I've just proven Q. Now I've plugged Q in with 2, so 6 and 2, same, C-E-L. And together, that allows me to infer R. Look at that. I just showed R. Now I showed R in this little subargument using direct derivation. Because within this little microscope here, microscopic universe, I just used direct derivation rules, conditional elimination. I used it twice, and I was able to infer R. Now I've marked off the show line. What this effectively does is like, look, I've shown R. Just ignore all this stuff because R is now in my premise set. That's great because I was trying to show R on the condition of P. And that's how I get if P then R. I assumed P is true. I was able to derive R. Now I'll bracket all this bad boy up. Boom, 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 boom. Because I've shown that if you assume P, then you can infer R, and that is it. I've proven if you assume if P then Q, and if Q then R, then you can infer if P then R. And I did this one, this second show, I did that using conditional derivation, the conditional derivation method. So I cite that by CD. And that, in a nutshell, is how you do conditional derivations. More schematically, for conditional derivation strategy, if you are ever asked to show something of a conditional form, conditional derivation, you should assume the first part, the thing that the arrow is pointing from, and then show the thing the arrow is pointing to. Every single time. So whatever you have up here, if you need to show something that looks like this, phi then chi, I'm using the schematic letters. First thing you do, every single time, it's a recipe. Don't overthink it. Assume the thing the arrow is pointing from. Add a show line for the thing it's pointing to. Then try to apply your rules. That's it. You box this up when you're done. You mark that off. You box the whole thing up when you're done. You mark that off and you are done. Conditional derivation. Don't overthink it. You will. Don't. Keep on guard. Anytime I'm asking you to show something that says if P then this, if P then Q, if R then Q, if R then S, always just say that's a conditional derivation. I have to assume the first part and try to prove the second every single time. Okay? I'm serious. You'll forget. Don't.